for our final lesson within this first section of Unit 8 on matrices, we're looking at basically matrix inverses. There's a couple of components here. We've got identity matrices and reciprocals and inverses. So if we get started just right on that first page within our notes, the first question just asks us to consider the two matrices A and B. And they're similar. I mean, they got same numbers, a couple of different signs and things, but it does ask us to take the multiplication of A times B. So we're going to do that first. So that looks like this. We're going to say, B there. Let's see. All right, so remembering we take our first row and our first column, and we're lining them up when we say 4 times -2 plus 3 times 3. So -8 plus 9. And then first row, second column, we take 4 times 3 plus 3 times -4. That's 12 minus 12. And then we go to the second row. So we go second row, first column. So 3 times -2 plus 2 times 3. So that's -6 plus 6. And second row, second column, we take 3 times 3 plus 2 times -4. So that's 9 minus 8. Our ending matrix then, that's a 1 here. That's a 0, 0, and 1. And that was no accident. Those two matrices, A and B, have a very specific relationship to each other. In fact, what we would say is that matrix B is the inverse of matrix A. All right. So we've introduced a new term, the term of being an inverse of a matrix. So again, anytime you would be able to take matrix A times B, and you end with this specific type of matrix, it is its inverse. So what we're going to call this type of matrix, where it's 1 here, kind of down the diagonal, we're going to get 1s. Everywhere else, we'd fill in with 0s. So down here, that's our new term. It's an identity matrix. So this matrix here is the identity matrix. I said the identity matrix. What I mean is it is an identity matrix because there are more than one of them. By definition, any square matrix, so the first thing is it has to be a square matrix where there is a 1 for each entry along the main diagonal. The main diagonal is that from top left going down to the right. So if every entry along that diagonal is a 1 and every other entry is a 0, it is considered an identity matrix. Okay, and it is specifically an identity for matrix multiplication. So example we have already here, but they show it again for a 2 by 2. The same thing though, if you look at a 3 by 3 matrix, its identity matrix is all 1s along the diagonal and then 0s everywhere else. We will use that for systems of solving equations later on. What we're trying to do is that, because if you think about, this would be equation 1, and then these are my x, my y, and my z. So if I have 3 variables, and I have x here, I don't want to find any y's or z's because it's one equation with multiple unknowns. But here, if I took this times that matrix, see, if I were to take that times x, y, z, Let's see, is that right? Nope, sorry, I did that wrong. If I were to reorder it, I guess, if I were to do, I guess I could do it this way, x. See, I could have written them horizontally ahead of this, a times b, and that would have worked out. But here I'm saying 1 times x, and then 0 times y, 0 times z. So that would actually get me just an x equals term. That's how, we'll get into that later, but that's how this identity matrix is useful, is by isolating our variables. All right, going further. A little bit about our notation. So the example shown above, we called it matrix B. The second matrix, matrix B, we're calling that the inverse of A. Well, that was because we were introducing the concept. If we actually wanted to refer to that matrix, matrix B, as the inverse of A, we don't call it a new letter. What we actually need to call matrix B, if it is in fact the inverse, we would call it A inverse. We don't call it matrix B, we call it A inverse. And there's a notation for that, just like we would have x to the minus 1 or 8 to the minus 1. That is the inverse function to have a negative exponent. So when we refer to a matrix or matrices inverse, we would say whatever the original matrix, in this case A, to the minus 1. All right, so it says when you can find the inverse of matrix A, the following is always true. If you take A times its inverse, you will get the identity matrix. So to bring this back to linear algebra, if you wanted to see where have we seen this before? If you look at A times A inverse, think about it like this. Say we had 8. So instead of A, we have number 8. So we take 8 times its inverse. Its inverse would be 8 to the minus 1. So what that looks like is 8 times, instead of 8 to the minus 1, that's really 1 over 8 to the positive 1, or just 1/8. If we take A times its inverse, we get the identity. If we have numbers in linear algebra, we would have 8 times its inverse, and we get 1. 8 times 1/8 is 1. The same thing's happening when we're taking A times A's inverse. We're getting the equivalent of a 1 in linear algebra for our matrix algebra. We're getting that identity matrix where all we have is 1s and 0s. So that's where we're coming from. That's how we can tie this back to what we've learned over the last several years of math. So in general, how do you find the inverse of a 2x2 matrix? So how did we get matrix B? That wasn't just a guess. It was a mathematical calculation. So in order to get matrix B up here, the -2, 3, 3, -4, what you do is to find the inverse, you take and find its determinant. So we did that yesterday. We found the determinant. We say A times D minus B times C. Okay, so that's 1 over A times D minus B times C times, and then all you do is you switch the order or the positions. So you switch the positions of A and D. So now this is a D and this is an A. So we switch those, and then you change the sign of the other two entries. So whatever, if that was already a negative number up here, you'd turn it positive, and same thing here. But so you flip the positions of A and D, and then along the other diagonal, you just flip its signs. And that's how you get an inverse. So let's do an example. It looks like we already did find the example here on this one, but the inverse of matrix, well, we'll call this C. We're working with a new matrix. So matrix C, to find its inverse, you take the determinant, so 4 minus 6. The determinant is first diagonal minus second. 4 minus 6, that's -2. So from up above, if I can get this to go up a little bit, there we go. We said the inverse is 1 divided by the determinant. Well, the determinant was -2, so we take 1 divided by negative 2. And then we take that times that matrix where we switched these orders. So 1 and 4 switch places. So now we have 4 and 1. And then we just keep these in the same position, but we change their values from positive, negative, or negative, positive. So this would be negative 2 and negative 3, which you see here. So now what we have is we're taking a scalar multiplier, which we learned how to do a few days ago, times a new matrix, and we get, well, negative 1/2 times 4 is negative 2, and then negative 1/2 times negative 2 is 1, and negative 1/2 times negative 3 is negative 3, positive 3/2, sorry, the negatives canceled, and then negative 1/2 times 1, we get negative 1/2. So now, this matrix right here is considered C inverse, C to the minus 1. Okay, we can check this. We can say, I'm just going to do it down here momentarily. We're going to say, let's see, 1, 2, 3, 4. Okay, so there's our matrix. Now, by definition, we should be able to multiply by the inverse and get the identity matrix. So then it's negative 2, 1, 3/2, and negative 1/2. All right, so let's see what happens. When we multiply these, we say 1 times negative 2, 1 times negative 2, plus 2 times 3/2, so plus 3. Then we say the first row, second column, so 1 times 1, 1 times 1, plus 2 times negative 1/2. 2 times negative 1/2, that's negative 1. Then we go to, what happened there? Then we go to our second row, first column. We say 3 times negative 2, negative 6. And then we've got 4 times 3/2, that's 12/2, or plus 6. Then second row, second column, 3 times 1, plus 4 times negative 1/2, so minus 2. Negative 2 and 3 is 1. 1 minus 1 is 0. Negative 6, 6, 0. 3 minus 2 is 1. So we can confirm exactly that. Looking ahead to I'm not sure if it even noted in here, but what I know about matrices is that not only do we know that it is an inverse if A times A inverse gives us the identity, we should also be able to take A inverse times A. We should be able to switch the order. Remember before, when we did multiplication with matrices and we did A times B, we got a new matrix. If we took B times A by switching the order of the matrices, sometimes it doesn't even work. Sometimes you can't even multiply it. But if you can multiply and get another matrix, A times B gives you one matrix product. B times A will give you a different matrix product. Sometimes it's the same, but 9 times out of 10 it's not. So in order for a matrix to be the inverse of another matrix, you have to be able to take the order A times A inverse and get the identity, but also be able to take A inverse times A and switch the order and still get the identity matrix. So let's, hold on. Let's see, we're almost out of time actually. So I'm going to do this as a second video. So part 2 will be finishing up this lesson.